Hi, I'm Bob. Welcome back to the 5 Minute Econometrics, a program designed to help you better understand basic econometric concepts and estimation ideas. Today, we will explore T-statistics. We need T-statistics when we perform the t-tests after the OLS regression. For the population model, we will never know the parameters with certainty. Instead, we can hypothesize about the value of a parameter and then use the statistical inference to test our hypothesis. To construct hypothesis tests, we need the T-statistics. T-statistics are commonly used in statistical inference and regression analysis. We can obtain a t-distribution from a standard normal variable and a chi-square random variable. The random variable t has a t-distribution with n degrees of freedom if its numerator has a standard normal distribution and its denominator has a chi-square distribution with n degrees of freedom. From previous topics, we know that under 6 classical linear model assumptions, the OLS estimator beta hat is normally distributed. After we standardize a normal random variable by subtracting its mean and dividing by its standard deviation, we obtain a standard normal random variable. That is expression 1. On the other hand, we know that the estimate of error variance, sigma hat squared, can be computed by the sum of squared residuals. So, expression 2 has a chi-square distribution. By definition, we can show that the following expression has a t-distribution. It is the formula we used to calculate the t-statistics. For a linear regression model, such as the one that relates workers' hourly wages to their educational attainment, health status, and their parents' income during their childhood years, we can use t-tests to find whether an explanatory variable has a significant effect on the outcome variable. For example, we want to determine whether education is associated with higher hourly wages. The null hypothesis is that beta 1 equals 0. The alternative hypothesis is that beta 1 is greater than 0. We apply the OLS method to the linear regression model to determine whether there is sufficient evidence to reject the null hypothesis. The null hypothesis, beta 1 equals 0, means that after controlling for all other explanatory variables in the model, the variable of interest has no effect on the expected value of the outcome variable. In our model, the null hypothesis means that one's health and parents' income have been accounted for. Education has no effect on workers' hourly wages. If the null hypothesis is true, it implies that people's family background is much more important than their educational attainments. High wages are associated with the wealth of their parents, rather than the number of years of schooling they receive. Those who grow up in wealthy families tend to earn higher wages in adulthood, regardless of their educational level. But if we can reject the null hypothesis, we conclude that education does increase people's earnings after considering the effects of family background. Here, we test whether beta 1 equals 0. So the T-statistic formula becomes beta 1 hat divided by the standard error of beta 1 hat, where beta 1 hat is the OLS estimator for beta 1. Since the standard error of beta 1 hat is an estimate of the standard deviation of beta 1 hat, the T-statistic measures how many estimated standard deviations beta 1 hat is away from zero. If it is far away from zero, it suggests that beta 1 is probably not zero, and we can reject the null hypothesis. The precise rejection rule depends on the alternative hypothesis and the chosen significance level of the test. The alternative hypothesis in our example is a one-sided alternative. A two-sided alternative hypothesis will be that beta 1 does not equal zero. The significance level is the probability of rejecting the null hypothesis when it is true. For instance, a 5% significance level means we are willing to mistakenly reject the null hypothesis when it is true 5% of the time. The T-statistic follows a T-distribution, as shown in the graph. We are looking for a sufficiently large positive value of the T-statistic in order to reject the null hypothesis that beta 1 equals zero in favor of the alternative hypothesis that beta 1 is greater than zero. This sufficiently large value with a 5% significance level is the 95th percentile in a T-distribution with n-k-1 degrees of freedom. It is called the critical value. We can find the critical values with a particular significance level and degrees of freedom directly from the statistical table. Our sample has 4,073 observations. N equals 4,073. The model contains 6 explanatory variables and 1 intercept. So the degrees of freedom equals 4,073 minus 6 minus 1 equals 4,066. It corresponds to an infinite degrees of freedom in the table. We find that the critical value with a 5% significance level and infinite degrees of freedom for one-tail test is 1.645. If the T-statistic is greater than 1.645, then we can reject the null hypothesis that education has no effect on hourly wages in favor of the alternative hypothesis that education contributes to earnings. Suppose the T-statistic is smaller than 1.645. We have no evidence to reject the null hypothesis at the 5% significance level against a one-sided alternative. Our regression results show that the T-statistic for schooling is 21.41, which is much higher than the critical value of 1.645, indicating that education has a significantly positive effect on hourly wages after considering workers' health status and family background. Each additional year of schooling increases wages by about 9% on average. Notice that as the significance level becomes smaller, the critical value increases. For the 1% significance level, the critical value becomes 2.326 in our case. A smaller significance level means we allow the null hypothesis to be rejected when it is true for a smaller probability, making the inference more accurate. But it also makes the rejection of the null hypothesis more difficult. The above is about the one-sided alternative and the one-tailed t-test. But it is more common to test the null hypothesis against a two-sided alternative. For our case of the workers' hourly wages, suppose we are uncertain whether education has a positive or negative effect on wages after controlling for the other variables in the model. We can perform a two-tailed t-test. The critical value for a 5% significance level with infinite degrees of freedom in a two-tailed t-test is 1.96. Our t-statistic is larger than that, so we reject the null hypothesis in favor of the alternative hypothesis. 1 more year of education increases hourly wages by 9% for workers whose health and parents' income are the same. This effect is statistically significant at the 5% level against a two-sided alternative. For the same significance level and degrees of freedom, the absolute value of the critical value against a two-sided alternative is larger than that against a one-sided alternative. It means it is harder to reject the null hypothesis in a two-tailed t-test than in a one-tailed t-test for the same significance level and degrees of freedom. In practice, we often perform the two-tailed t-test. Today, we have discussed the T-statistics. It's essential to remember that we are testing the hypothesis about the population parameters, that is the unknown parameters in the population model, rather than the OLS estimate. So it is beta that appears in the hypothesis. Beta hat will never appear in the hypothesis. The null hypothesis is that the parameter beta equals 0. We know that beta is also the expected value of the OLS estimator beta hat under classical linear model assumptions. The OLS estimator beta hat, subtracting its expected value and then divided by its standard error, follows the t-distribution. If the null hypothesis is true, that is, if the expected value of beta hat is 0, then the OLS estimator beta hat, subtracting 0 and then divided by standard error, has a t-distribution. That is why when we test whether a parameter is 0, the t-statistic is expressed as the beta hat divided by its standard error. Thank you so much for watching this video. See you soon. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.